Hi there, and thanks so much for joining me for this video. So in this video, I'm going to talk about two concepts that we haven't explored yet, and those are power and effect size. And these concepts are really important because they illustrate why we can't always trust the results of statistical tests. Or another way of thinking about it, I guess, is we can't always assume that the results of statistical tests are giving us the entire picture. So statistical power is the ability of any statistical test to detect a significant difference or relationship where one truly exists, right? So when we talked about statistical significance a couple of modules ago, we talked about different types of errors, right? And a type 2 error is one that happens when we conclude that there is no significant relationship between our variables, right? When in actuality there is a significant relationship, right? So power is very much related to a type 2 error. So power is simply 1 minus beta. And beta is going to represent the probability of a type 2 error, right? So if the probability of a type 2 error is high, right, then the power is low. If our power is low, then it means we might miss out on something interesting. We might miss out on a potentially significant finding. Okay, so how do we increase power, or how do we make our statistical test better able to detect a significant relationship if one exists? Well, the simplest way to do that is simply to increase our sample size, right? So if you don't have sufficient sample size or your study is underpowered, then it's going to be much harder for you to find a significant effect, even if one exists, right? So why is it that increasing our N or increasing our sample size is also going to increase our power? Well, as we talked about when we talked about sampling error, right? One of the best ways to decrease sampling error is to increase our sample size, right? Because the bigger our sample is, okay, the better able our sample is going to be to approximate the population parameter, right? So the more people we have in our sample, the more likely it is that our sample statistic, right, whether it be the mean or frequencies or whatever, it's more likely that our sample statistic is going to better approximate or be closer to the population parameter, right? And if our sample statistic is closer to the population parameter, then we're more likely to detect significant effects, okay? We can also increase our power through our research design. So in my last video, I talked about two different potential designs in reference to t-tests, right? So independent t-tests, because we're making comparisons between two different groups of people, right? That's a between subjects design. Whereas with a dependent samples t-test, we are comparing the same group of people at different points in time. And because we're making comparisons within the same individual over time, that's a within subjects design, right? And the primary advantage of a within subjects design is we're getting rid of pre-existing differences or individual differences, right? And individual differences between our participants is a source of error, or something that could make our sample statistic different than our population parameter. So getting rid of those individual differences or pre-existing differences is also going to make our test more powerful or better able to detect significant effects. Okay. But just like a potential statistical test can be underpowered, right, or not have enough participants, it's also possible for a test to be too powerful or overpowered, right? So generally speaking, having a bigger sample increases the likelihood that we'll get statistically significant results. But if our sample size becomes too large, even very, very minute differences will likely be statistically significant, right? And this is a problem because those significant differences might actually be very weak, right? And therefore not very useful or interesting, right? So a good rule of thumb to avoid having a statistical test or an experiment that is too powerful or not powerful enough is to have a sample size of approximately 30 to 40 people per group, right? So if you're looking at the influence of caffeine intake on memory, right, and you have a no caffeine condition, a low caffeine condition, and a high caffeine condition, then you would want a total of 90 to 120 participants in order to be optimally powered, right? So 30 to 40 people per group in your particular study. Okay. So effect size provide one way to indicate how meaningful a significant effect is. And how effect size does this is it quantifies what's referred to as the strength of the effect. Okay? And conveniently, every single statistical test that we've talked about in this course has its own measure of effect size. Okay? So the reason I waited to post this video until the time that you guys were preparing for the final exam is that it provides an excellent review of all the tests that we've learned this semester. Okay? So for each one, I'm going to tell you how to calculate and interpret the measure of effect size. And I'm also going to tell you not just how to calculate it by hand, but if applicable, how to find it in SPSS. So make sure you're paying attention to that part as well, because there will be SPSS questions on the final exam in addition to calculation questions. Okay, so one of the first tests that we talked about was the one-way chi-square test. Okay, so we use a one-way chi-square test when we have a single categorical variable and we're trying to get a sense of whether the percentages of the possible outcomes of that variable are different from what we expected. Right? So let's say we flip a coin 10,000 times and we expect 50% heads and 50% tails, but we end up with 50.99% coming up tails, right? So we would conduct a one-way chi-square test to see if a percentage of 50.99 is a statistically significant difference compared to the expected percentage of 50%. Okay? So let's say the results of our one-way chi-square test indicate that our coin, right, produced a statistically significant are significantly more than 50% tails, right? So essentially the difference between the observed 50.99 and the expected 50% tails is significant. Okay, so even though this is technically a significant difference, does it seem like a really important or meaningful difference? Probably not, right? 50.99 versus 50% is not really a huge difference. It's a fairly weak difference. Right? So for both the one-way and two-way chi-square test, our effect size is going to be indicated by phi. So to calculate phi, we use the formula. We would take our obtained chi-square value, divide it by the sample size, and take the square root. Okay? So if we flip a coin 10,000 times and get 5,099 tails, our effect size would be the square root of 3.92 divided by 100, right? So 3.92 is our obtained chi-square statistic, and 10,000 is our total number of flips, right, or our N. Okay, so that would give us a phi value of 0.02. Okay, so now that we know the formula for calculating phi, simply the square root of your chi-square value divided by n, how do we interpret that value? What does that 0.02 mean, right? Well, we have guidelines that we can refer to. So any number or any phi value that's less than 0.10 is considered a weak relationship, right? Whereas a phi value of 0.30 is considered a moderate relationship, and greater than or equal to 0.50 is considered a strong relationship, right? So although getting 50.99% tails when we expected 50% tails is statistically significant, it's not necessarily a meaningful or important finding, and in fact, it's a fairly weak effect as suggested by our guidelines, right? And if we look at the potential causes of getting a statistically significant finding, it's likely due to the fact that we have 10,000 observations, right? So that's quite a large N, and that's probably why we ended up with a statistically significant finding, even though it's a fairly weak effect. So let's look at the effect size for a two-way chi-square. So in our two-way chi-square example that we went over in class, we were looking at the potential relationship between extroverts or extroversion and smoking behavior, right? So we found in general that people who are extroverts are more likely to smoke than people who are introverts, or there's a greater percentage of smokers who are extroverts than smokers who are introverts, right? And our chi-square value was 13.24, and our p-value was less than 0.05, which indicates a statistically significant effect. Okay, so again, we're going to use that same exact formula to find our phi value or effect size value. We're going to take the square root of our chi-squared value and divide it by the total number of observations, or our sample size. Okay, so in order to do that, we would take our 13.24 value and divide it by 118, which is our sample size, and we would get 0.33. And based on the guidelines I just showed you, that suggests that there is a moderately strong relationship between smoking and extroversion. Okay? And there's an easy way to get your effect size using SPSS, right? So when you're in the statistics menu, when you run your chi-square test in SPSS, just check phi and Kramer's V in the stats menu, and that will give you your value of your effect size. Okay, so now let's talk about effect size for t-test, right? So we talked about 3 different types of t-tests, and fortunately, we would calculate the same value for all 3 types of t-test, and that is Cohen's d, right? And we have guidelines for Cohen's d as well. So if your d is equal to approximately 0.20, that indicates a weak relationship between your variables. If it's equal to, or if it's approximately equal to 0.50, that means there's a moderately strong relationship. And then greater than or equal to 0.80 would indicate a strong relationship. Okay? So let's go through this for each of our types of t-tests, right? So we started with a one-sample t-test in which we would compare our sample mean to a hypothesized population mean. And then we moved to an independent t-test where we were looking at 2 different groups of people on the same continuous outcome variable. And lastly, we compared the same people at 2 different points in time on some continuous dependent variable. Okay, for a one-sample t-test, Cohen's d is the difference between the sample mean and the population mean divided by the sample standard deviation, right? So one of the examples we worked through when you guys learned about the one-sample t-test was the study looking at whether or not a sample of students, a sample of introductory psychology students, had more siblings than a national survey of how many siblings most people have, right? So our sample had an average number of siblings of 1.80, and the population mean, the hypothesized population mean, was 1.65, right? And the sample standard deviation was 1.15. So our effect size, or our Cohen's d, would simply be 1.80 minus 1.65 divided by the sample standard deviation, which is 1.15. Okay, so we would get a value of 0.13. Okay, so in this particular case, there was not a significant difference between the sample mean and the population mean, so it's not surprising that the effect size would indicate that there's a very weak difference between the population and the sample. Okay? So SPSS doesn't have a button you can click to calculate the Cohen's d for you, but it's a fairly easy calculation, and SPSS will give you both the sample mean and the population mean and the sample standard deviation when you run a one sample t, so you can use those values to calculate the effect size. All right, so unsurprisingly, things are a bit more complicated for the independent t because we have to indicate the variability and the potential error for both groups, right? So each group, whenever we run an independent t-test, each of the group 1 and group 2 brings its own amount of error to the party, so we have to combine them, right? So to calculate Cohen's d for an independent t-test, we first need to find the pooled standard deviation. Fortunately, it's fairly easy to calculate, right? So we have df1, which corresponds to the degrees of freedom of group 1. We have df2, which corresponds to the degrees of freedom of group 2. And again, it doesn't matter which group you designate as group 1 or group 2. They're interchangeable as long as you keep them the same throughout the calculation, right? And then we square the standard deviation for group 1 and the standard deviation for group 2. And then we would divide all of that by the combined degrees of freedom, okay, and take the square root, okay? And once we have the pooled standard deviation, then we would plug that into our formula. So we would do the mean of group 1 minus the mean of group 2 over the pooled standard deviation. Okay, so again, unfortunately, SPSS doesn't have a button you can click that will do this for you, okay? But provided you have this information about your sample, you can calculate it by hand. Okay, for a dependent t-test, Cohen's d is simply the mean of the difference scores divided by the standard deviation of the difference scores. Okay, and so again, SPSS won't calculate these for you, but they will give you the mean and standard deviation for the difference scores. Right? So in that case, your mean is 20.18 and your standard deviation is 151.41 or 42, excuse me. So if you round those and then divide the mean by the standard deviation, you end up with 0.13. Okay, and again, your Cohen's d indicates a weak effect, which isn't surprising because if we look at the significance value or the p-value, okay, it's 0.094, which indicates that it's not a significant effect. All right. So this concludes my review of all of the tests we have conducted this semester and how to calculate effect sizes in both SPSS and by hand. So certainly if you have any questions, feel free to contact me, and I hope you have a great day.